Imagine for a moment a world where your favorite online services, the ones you rely on every single day for streaming movies, online banking, all that stuff, suddenly just stopped.
Right.
Not for like a minute, but for hours or even
Oh,
days.
yeah, that'd be chaos.
Exactly. In our hyper-connected digital age, keeping things running isn't just like an advantage, it's the absolute bedrock of modern business and, well, our daily lives. But how do we actually ensure that these services, especially the ones living out there in the cloud, are always available?
It's a huge challenge, and it's only getting more complex.
Yeah.
We've got more data, more users, higher expectations all the time. It's not just about stopping failures anymore.
Right.
It's about engineering systems that can, well, survive and even thrive when things inevitably go wrong. It's kind of the unsung hero behind every click, every transaction.
Absolutely. So today we're taking a real deep dive into this critical world of business continuity, and we're focusing specifically on this essential lesson, cloud service availability. Think of it as peeking behind the curtain. Yeah. Understanding the magic, the engineering that keeps your digital world spinning even when stuff happens.
Exactly. Our mission for you today is to really unpack the core concepts, the clever mechanisms, the strategic planning, basically everything that goes into making sure cloud services are consistently available, reliable, and secure.
We'll cover how availability is measured, those nines we hear about.
Right, the nines. And also the techniques used to guard against outages, data loss, the whole package.
You'll walk away not just informed, but hopefully with a new appreciation for this digital backbone we all depend on.
We've been digging into a pretty comprehensive guide on cloud infrastructure and services, pulling out the key insights for you.
Okay, so let's get started. Let's unpack this. All right, let's start with the basics. When we talk about cloud service availability, what does available actually mean? It sounds simple, like on or off.
Yeah, it sounds simple, but it's really not just on.
Right. It feels more complicated than that.
It definitely is. Available in the cloud context means a service can perform its agreed-upon function. That's the key part. It has to meet business needs, customer expectations during its operational time.
So it's not just up, it has to be working properly.
Exactly. It's about being consistently ready and functional. Like a banking app isn't really available if you can log in, but you can't transfer money. Right? The core function isn't working.
Makes sense. It has to do what it's supposed to do. So what does this idea rest on? What are the main pillars supporting availability?
Well, it hinges on several critical pillars. They all need to be solid. First, there's the reliability of the underlying cloud infrastructure itself.
The nuts and bolts.
Yeah, the compute VMs, containers, the storage systems holding the data, and the network tying it all together. If any of that's shaky, the service on top is unstable.
Okay.
Second, you've got the robustness of the business applications, the software running on that infrastructure. It needs to be built resiliently.
Because the app itself has to be tough.
Right. It can't just assume the infrastructure is perfect. And third, crucially, the availability of the data itself.
Yeah.
If the data isn't there or isn't right, the app can't work, even if everything else is fine.
Got it. Infrastructure, application, data. All three need to be working together.
This whole ecosystem, yeah.
Okay, so when we try to measure this, especially in contracts and stuff, we always hear about the nines. What exactly are the nines? Why is that the shorthand?
The nines. It's a practical way, a standard way, to quantify service availability. It tells you how much uptime a service guarantees, usually over a year.
Like a percentage.
Exactly. It's
Yeah.
percentage shorthand. So 5 nines availability means the service promises to be available 99.999% of the agreed service time in a year. It's a very precise target.
Okay, 5 nines, 99.999%. That sounds almost identical to, say, 3 nines, which is 99.9%.
That's tiny.
But I've heard that tiny difference in percentage points has a massive real-world impact. This is where it gets really interesting for me. What does that actually mean in terms of downtime, like minutes or hours?
Oh, the difference is absolutely huge. It's often counterintuitive. Let's break it down. 5 nines, that 99.9999%. That translates to an allowable downtime of just 5 minutes and 15 seconds.
Per year.
5 minutes a year. That's it.
That's it. Less than 6 minutes total outage time allowed in 365 days. Now compare that to 3 nines, 99.9%. That allows for over 8 hours and 45 minutes of downtime annually.
Wow. Okay, that's night and day. 5 minutes versus nearly 9 hours.
Exactly. So that 0.0999% difference might look small, but it's almost 100 times more downtime potential. For critical services, think healthcare. Finance, that difference is enormous. It could mean millions, even billions in losses or huge risks.
Like, it really puts it into perspective. And I guess the higher the nines, the more complex and uh, expensive the whole setup behind it must be.
Absolutely. Achieving those extra nines requires significantly more investment in redundancy, automation, monitoring, everything.
So how do they actually calculate this? Is there like a standard formula providers use? There is, yeah, and it's pretty straightforward. It's the basis for SLAs, service level agreements. The formula is you take the agreed service time, subtract the downtime, then divide that by the agreed service time and multiply by 100.
Okay, so agreed service time downtime, agreed service time x 100.
That's the one. Gives you the percentage of time the service was actually up and running as promised. Very transparent.
Let's try a quick example. Our source material mentions a data backup service. Let's say it's supposed to run 247, 365 days a year.
Okay, so that's 8,760 hours in a year. That's your agreed service time.
Right. Now imagine this service had a couple of failures during the year, totaling, say, 3 full days of downtime.
Okay, 3 days. That's 3 times 24, so 72 hours of downtime.
Right. So plugging that in, 8,760 minus 72, divided by 8,760 times 100.
Let's see. That comes out to roughly 0.9918. So 99.18% availability for the year.
99.18%. See, that really shows it. 3 days out of 365 sounds maybe not that bad in isolation, but it knocks you way down from those high nines. You're barely above 2 nines there.
Exactly. It highlights why those SLAs are so important and why achieving consistent high availability is so difficult. Even small outages add up quickly against those percentages.
And for you listening, understanding this helps you see what those SLA numbers actually promise in real terms.
Definitely.
Okay, so we know what availability is, how it's measured. But why do services actually go down? When things go wrong, what are the usual suspects?
Good question. We can group the causes into 2 big buckets: unplanned events and maybe surprisingly planned activities.
Unplanned first. That's probably what most people think of, like sudden problems.
Like the unpredictable stuff. This covers everything from hardware failures,
Yeah.
a server dying, a storage drive failing, a network switch glitching out, to software bugs. Those can be insidious, maybe a hit or flaw in the application code that only shows up under heavy load.
Yeah.
And then there's human error, still a big one.
People messing up.
Yeah, unfortunately. Someone accidentally pulls the wrong network cable, misconfigures something critical, deploys buggy code without enough testing. It happens, even with the best processes.
And it's not just stuff inside the data center, is it? External things can cause major problems, too.
Absolutely. Yeah. Bigger picture things. Widespread power outages affecting a whole region, natural disasters, floods, earthquakes, hurricanes. Those can physically destroy infrastructure.
Yeah, that makes sense.
And of course, the ever-present threat of cyber attacks. Things like ransomware that encrypts everything, or massive DDoS attacks that just overwhelm services, or even targeted intrusions. These external factors are often harder to control.
Okay, so that covers the unexpected. But you mentioned planned activities can also cause downtime. That seems counterintuitive. If it's planned, shouldn't it be seamless?
You'd think so, and that's always the goal. But it's not always achievable, especially for major changes. Even necessary routine activities carry some risk.
Like what kind of activity?
Think about major application upgrades, big database reorganizations that might need exclusive access, replacing core hardware that can't be swapped out live, migrating huge amounts of data to a new system, or even moving services to a totally different data center.
Right. Those sound disruptive.
They are essential for keeping things up to date, secure, and performant in the long run. But each one involves risk. You plan meticulously, you test, you have rollback plans. But achieving zero downtime during complex maintenance is really hard and often extremely expensive. Sometimes a brief maintenance window is unavoidable or the most practical choice.
Okay, so we've got all these potential failure points, unexpected hardware glitches, bugs, human errors, external disasters, even planned maintenance. How do cloud providers actually build resilience against all this? What are the core strategies?
The main goal is always to minimize disruption, or ideally prevent it affecting the user. And the absolute foundation for almost all solutions is redundancy.
Redundancy, meaning having spares for everything.
Pretty much, yeah. Duplicating critical components. And not just within one data center, like having extra servers, multiple network paths, redundant storage controllers, but also, really importantly, across different physical locations. Different data centers, often called sites or availability zones, sometimes in completely different regions.
So if one whole building has a problem,
Exactly. If one site goes down due to, say, a power outage or a local disaster, another site is ready to take over. This multi-level redundancy creates fault tolerance. It means no single point of failure should bring everything crashing down. That's how you get those high nines.
makes sense. Beyond the systems themselves, what about protecting the data? Because if the data's gone or corrupted, the service is toast anyway.
Data protection is absolutely non-negotiable. You need things like backup and replication. Creating copies of data.
Multiple copies.
Yes, usually both locally, within a site for quick recovery from small issues, like accidental deletion, and remotely, across different sites. So even if your primary data gets wiped out or hit by ransomware, you can restore services quickly from a clean, mirrored copy somewhere else. It's your ultimate safety net.
And when a failure does happen, you don't want engineers scrambling manually to switch things over, right? That sounds slow and error-prone. That's where automatic failover comes in.
Right, that's the goal, automation. Systems are designed to automatically detect when a component, or even a whole site, fails. We're talking milliseconds sometimes.
Wow.
And then they automatically redirect traffic, workloads, whatever's needed, to a healthy, redundant resource. This slashes downtime and reduces the need for manual intervention, making recovery faster and more reliable.
So like scripts that spin up a new VM if one crashes?
Exactly, that kind of thing.
Right.
Or automatically rerouting network traffic to a different server or even a different data center if the primary one isn't responding, building self-healing capabilities in.
And you mentioned earlier it's not just the infrastructure. The applications running on top need to be resilient too.
That's a really critical point.
Huh.
Developers need to design applications expecting failures. They can't just assume the infrastructure beneath them will always be perfect.
So the app needs built-in smarts.
Yeah, logic to handle issues gracefully, maybe retry a failed operation or switch to a backup data source, or even operate in a slightly degraded mode instead of just crashing completely. Resilient architecture at the application level is key.
And finally, when a really big disaster hits, something beyond a typical component failure, we hear about disaster recovery, or DR. How does that fit in with business continuity, BC? Are they the same?
They're tightly linked but distinct. Business continuity BC is the big picture, the overall strategic plan for keeping the business running during and after any disruption. It covers people, processes, technology, everything.
Okay, the whole strategy.
Right. Disaster recovery, DR, is a crucial part of BC, specifically focused on recovering the IT systems and infrastructure. So when a major disaster hits, like that regional power outage taking out a data center, the BC plan triggers the DR process.
I see.
That DR process involves coordinated steps, often both automated and manual, to get the IT services back online at an alternate functioning location. It's about moving users, data, and services seamlessly to keep the tech side running. BC is the what, DR is the how for IT recovery.
Got it. That clarifies the relationship. Building on that, let's dig deeper into fault tolerance. You mentioned it earlier. What exactly is it, and how is it different from just, say, high availability?
Good distinction to make. Fault tolerance is a step beyond basic high availability. High availability focuses on minimizing downtime, getting things back up quickly after a failure. Fault tolerance, though, is the ability of a system to continue performing its functions without any interruption, even when some parts fail.
So, zero interruption. The failure is essentially hidden.
Ideally, yes. The failure could affect infrastructure parts, maybe even cause slightly degraded performance or output, but the service itself keeps running. The core idea is that a single fault shouldn't take the whole thing down. The system absorbs the hit and carries on.
Okay. Handling failure so gracefully, the user might not even notice. What kind of faults are we usually trying to protect against here?
It's the usual suspects, really. Hardware failures are common: a disk drive dying, a server power supply failing, a network card malfunctioning. Then you have software bugs, coding errors that cause crashes or weird behavior, and still administrative or user errors. Human mistakes during configuration, updates, day-to-day stuff. Fault-tolerant systems need to anticipate and handle all of these.
And our source material broke down the types of unavailability that fault tolerance aims to combat. Can you remind us of those? They seem distinct.
Sure. Fault tolerance tackles three main types. First is transient unavailability. This is like a quick one-off glitch, maybe an online purchase times out due to a brief network hiccup, but works fine when you retry, often self-correcting.
Okay, temporary blip.
Second, intermittent unavailability. This is more annoying. Recurring outages that come and go. The service is up, then down, then up again. Really frustrating for users and often points to a tricky underlying problem.
Right, unpredictable.
And third, permanent unavailability. This is the worst case. The service stays down until the broken component is physically fixed or replaced, like a cut fiber optic cable or a critical bug that keeps crashing the application until it's patched. Fault tolerance aims to prevent or mask the effects of all three.
Makes sense. So how is this fault tolerance actually achieved in these complex cloud systems? Is there a single method?
It's usually a mix. It can be done through clever software design, specialized hardware built for resilience,
Hmm.
or most often a combination of both working together.
Okay.
But here's a key thing to understand. Achieving 100% fault tolerance across an entire system, making it truly infallible, that's incredibly difficult and usually prohibitively expensive.
The law of diminishing returns.
Exactly. The closer you get to perfect fault tolerance, the cost and complexity tend to shoot up exponentially. So businesses usually aim for a specific level of fault tolerance based on the criticality of the service, balancing the cost against the risk of downtime. It's a strategic trade-off.
And just to be clear, how does fault tolerance connect back to reliability and availability? Are they the same thing in practice?
They're different but deeply connected. Fault tolerance is what improves both reliability and availability. Reliability is about how consistently a system performs when it's working. Availability is about whether the system is ready to perform when needed.
I see.
Fault tolerance boosts both by making sure the system stays operational and ready, even when individual parts fail. It's the engineering foundation that supports high reliability and high availability metrics.
Okay, let's get into the nitty-gritty then. What are some specific infrastructure-level techniques used to achieve this fault tolerance? Starting with compute, keeping the brains of the operation alive.
Right, compute redundancy is fundamental. A core technique is compute clustering. This is where you group two or more physical servers or, more commonly now, hypervisors, the software managing virtual machines so they act like a single logical unit.
They work together.
Exactly. They constantly monitor each other using something called a heartbeat signal over a private network link. If one server stops sending its heartbeat, the others know it's in trouble and can take action immediately.
And within clustering, I know there are different ways to set it up, like active-active versus active-passive. What's the difference there?
Good question. In active-active clustering, all the servers, or nodes, in the cluster are actively running services and balancing the incoming workload simultaneously. If one node fails, the remaining active nodes just pick up its share of the work. This boosts both performance, because you're using all the resources, and availability, because failover is seamless.
Sounds ideal, but maybe more complex.
It can be, yeah. Managing load balancing and data consistency across active nodes takes careful setup. The alternative is active-passive clustering. Here you have one or more active nodes running the service and one or more passive nodes just standing by, waiting.
Like a backup.
Exactly. The passive node only takes over if an active node fails. This provides high availability through failover, but it doesn't usually improve performance during normal operation because the passive node isn't doing any work until needed. It's often simpler to manage, though.
Okay, that makes sense. Another compute technique mentioned, especially relevant for hybrid setups, is cloud bursting. How does that fit into availability?
Cloud bursting is a really neat capability of hybrid cloud. The idea is your application normally runs in your private cloud or on-premises data center. But if you get a sudden, unexpected surge in demand,
Like a Black Friday sale.
perfect example, or maybe a viral marketing hit,
Yeah.
instead of your local systems getting overwhelmed and failing, the excess load automatically bursts out to a public cloud provider. You temporarily use their resources to handle the peak.
So it scales on demand.
Right. It ensures the service stays available during those peak times without you having to build and pay for massive amounts of infrastructure that sits idle most of the year. It's cost-effective elasticity.
Okay.
But you do need to think about data security, compliance, and potential latency when moving stuff between your environment and the public cloud.
Gotcha. And are there specific product examples that showcase these compute fault tolerance ideas, like from virtualization vendors?
Oh, definitely. Virtualization platforms are central here. VMware, for example, has vSphere HA, high availability. If a physical host running VMs fails, vSphere HA automatically restarts those VMs on other healthy hosts in the cluster. It minimizes downtime.
Okay, it restarts them.
But then they have vSphere Fault Tolerance, FT, which goes a big step further. It creates a live shadow copy of a VM on a separate host running in perfect lockstep with the primary.
A live shadow.
Yeah. Every instruction executed on the primary is mirrored on the shadow. If the primary host fails, the shadow instantly takes over with zero downtime and zero data loss. It's continuous availability for the most critical VMs. Very powerful stuff.
Wow, that's impressive. Okay, moving on from compute. Network problems can bring everything down too, so network redundancy must be just as crucial.
Absolutely critical. Even a brief network outage can have a massive ripple effect. So the network infrastructure has to be redundant. One common technique is link aggregation.
Aggregating links, combining them.
Exactly. You take multiple physical network links, say cables connecting to two switches, and bond them together so they act as a single, higher bandwidth logical link.
What's the benefit?
Two main things. First, performance. It increases the total available bandwidth by spreading traffic across all the physical links. Second, fault tolerance. If one physical link in the group fails, traffic automatically continues flowing over the remaining links without interruption. So if you bundle three 10-gig links, you get up to 30 gig throughput, and it can survive one or even two links failing.
Okay, that makes sense at the switch level. What about on the actual servers? I think I've heard of NIC teaming.
NIC teaming is very similar, but it happens on the server itself. You group multiple physical network interface cards, NICs,
Right.
in a server, and they appear as a single logical NIC to the operating system, or hypervisor.
Same benefits.
Pretty much. It provides network path failover if one NIC or its cable fails, preventing the server from losing connectivity. And it can also aggregate the bandwidth of the teamed NICs, giving the server more network throughput. It's about making the server's connection to the network resilient.
So multiple paths out from the server, multiple paths between switches. What about getting data reliably to the storage systems? That seems like another potential bottleneck.
Definitely. And that's where multipathing software comes in.
Okay.
It allows a server or compute system to use multiple physical paths to connect to the same storage volume, often called a LUN, on a storage array.
Multiple routes to the data.
Exactly. Think of it like having several different roads to get to the same destination. If one path fails, maybe a cable gets cut, an adapter fails, or a switch port goes bad, the multipathing software automatically reroutes the storage I/O over the remaining healthy paths.
Seamless failover again.
Right. It prevents a single path failure from disrupting access to critical data. Plus, good multipathing software can also balance the I/O load across all active paths during normal operation, improving storage performance by preventing any single path from becoming overloaded. It's crucial for reliable and fast storage access.
Okay, we've hit compute and network fault tolerance. Now storage itself. Drives fail, controllers fail. How do we make the storage systems resilient?
Yeah, data unavailability due to storage failures is a huge concern. One powerful approach, especially in complex environments, is storage resiliency using virtualization.
Storage virtualization. How does that help fault tolerance?
Well, you put a virtualization layer, often a dedicated appliance or software, within the storage area network, SAN, between your servers and your physical storage arrays. This layer abstracts the physical storage.
It hides the physical details.
Exactly. It creates a unified pool of storage from potentially many different types or brands of physical storage systems. Then you create virtual volumes, LUNs, from this pool. The clever part is you can then mirror these virtual volumes across different physical storage systems.
So the mirror's on a completely separate box.
Right. So if one entire physical storage array fails, the virtualization layer seamlessly redirects all I/O to the mirrored copy on the other array. The servers don't even know the difference. It provides high availability even if a whole storage system goes down.
That sounds very flexible. What about erasure coding? We hear that term a lot now, especially with object storage and distributed systems. How does that provide fault tolerance differently?
Erasure coding is a really important technique, particularly for large-scale storage. It provides data redundancy in a much more space-efficient way than traditional mirroring or RAID. More efficient than making full copies.
Yes, significantly. Instead of making, say, 2 or 3 full copies of the data, erasure coding breaks the data into smaller fragments. Then it calculates some extra coding or parity fragments based on the original data fragments.
Like mathematical checksums.
Kind of, yeah. These data fragments and coding fragments are then spread across many different drives or even different servers, nodes, in a distributed system.
So it's scattered around.
Right, and the clever math behind it means you can lose a certain number of any fragments data or coding and still reconstruct the original data perfectly. For example, a common setup might break data into, say, 9 pieces and create 3 coding pieces in M9K3 scheme. These 12 total pieces are stored across 12 different drives or nodes. The system can then tolerate the failure of any 3 of those 12 drives and still get the data back.
Wow, that's more resilient than typical RAID. Often, yes, and usually with much less storage overhead than simple mirroring. You're storing 12 pieces instead of maybe 18 or 27 for full copies. That efficiency is why it's so popular in massive cloud storage systems. Higher fault tolerance at a lower storage cost.
Okay, that covers the infrastructure layers really well. But you stressed earlier that applications themselves need to be resilient. They can't just rely on the infrastructure being perfect. What are the key techniques developers use for application resiliency?
That's right. The application has to be failure aware. One important design principle is graceful degradation.
Degrading gracefully, meaning it doesn't just crash.
Exactly. It maintains some level of functionality even if parts of it or services it depends on are unavailable. Instead of just throwing an error and dying, it adapts.
Can you give an example?
Sure. Think about an e-commerce site again. If the external service that provides product recommendations goes down, a gracefully degrading site wouldn't just stop working. It might simply hide the recommendations section but still let you browse, search, and buy products. Or, like we discussed, if the payment gateway fails, it might let you add things to your cart but just disable the final payment step temporarily, maybe with a helpful message.
So it keeps the core functions running if possible. Minimizes user disruption.
Precisely. It preserves as much of the user experience as possible rather than just giving up.
What about handling those temporary glitches, those transient errors we talked about? An app calling another service that just blips out for a second.
For those, you need fault detect and retry logic built into the application code. When an application makes a call to another service and it fails, maybe with a network timeout or a service-busy error, the code shouldn't just give up immediately.
Should try again.
Right. Implement logic to automatically retry the operation after a short pause. Often, the temporary issue will have resolved itself and the retry will succeed. A common pattern here is exponential backoff.
Exponential backoff.
Yeah, it means the delay between retries increases each time. So maybe wait 1 second, then 2 seconds, then 4, then 8. This prevents the failing application from hammering the potentially overloaded service with constant retries, giving it a chance to recover.
Smart. Okay, what about user sessions? We've all had that frustration of a website forgetting our shopping cart or logging us out unexpectedly if something glitches. How do resilient apps handle that?
That's addressed by using a persistent state model. Traditionally, web applications stored session information, like your shopping cart, in the memory of the specific server handling your requests. If that server crashed, your session state was lost.
Yeah, annoying.
Modern resilient applications avoid this. They're either designed to be stateless, meaning each request is independent and contains all needed info, or, more commonly for user sessions, they externalize the state. They save the session data, shopping cart, login status, etc., to a separate, shared, persistent storage system, like a database or a distributed cache, that all application servers can access.
So the state lives outside the server.
Exactly. If the server handling your request fails, your next request just goes to another healthy server, which can instantly retrieve your session state from that external store. Your shopping cart is still there, you're still logged in. It makes individual server failures invisible to the user and is crucial for scaling out.
That makes perfect sense. And what about checkpointing? It sounds like saving your progress in a game.
It's a very similar concept. Checkpointing involves periodically saving the entire current state of an application, or at least its critical data and processing state, to persistent storage.
Like a snapshot of the running application.
Pretty much. If the application then fails for some reason, instead of restarting from scratch, which might involve replaying hours of transactions or losing work, it can restart from the last saved checkpoint. This significantly reduces the amount of lost work and dramatically improves the recovery time objective, RTO, how fast you can get back online.
But I guess saving the entire state frequently could slow things down.
That's the trade-off. More frequent checkpointing means less potential data loss and faster recovery, but it also adds overhead and can impact the application's real-time performance because it's constantly writing its state out. So you have to tune the checkpoint frequency based on how critical the application is and how much performance impact is acceptable.
Okay, we've covered availability and fault tolerance extensively. Let's shift focus slightly to data protection itself. Beyond just keeping services running, why is protecting the actual bits and bytes so fundamental?
Because ultimately, the data is often the most valuable asset. Even if your service infrastructure is perfectly available, if your data gets lost, corrupted, or stolen, you're in massive trouble. Data protection is about creating copies, ensuring you can recover that data if the original is compromised.
And it's not just about having one copy, right? Location matters.
Absolutely. You need protection both Locally, maybe within the same data center, for quick recovery from minor issues like accidental deletion or a VM corruption, and critically at remote locations. Geographically separate sites. If you need to fail over your entire service to a different region due to a major disaster, your data must be available there, ready to go, to actually make that failover work.
And I imagine not all data needs the same level of intense protection. That sounds expensive.
You're right, it would be. That's why organizations use a tiered approach to data protection. You classify your data and applications based on their business value and criticality.
Like gold, silver, bronze tiers.
Exactly like that. Tier 1 is your mission-critical stuff. The services and data the business absolutely cannot function without. These get the most stringent and usually most expensive protection, aiming for a near-zero data loss, RPO, and super-fast recovery, RTO, maybe minutes. Think core banking systems, emergency services dispatch.
Okay.
Tier 2 might be important, but less time-critical services, maybe internal collaboration tools, or less critical customer databases. Here, the Arporto targets can be a bit more relaxed, maybe hours instead of minutes, using less costly protection methods.
And tier 3.
Tier 3 is typically for non-critical data, historical records, development environments, things where less frequent backups and longer recovery times, maybe days, are acceptable. This tiered approach lets you focus your resources effectively, spending the most to protect what truly matters most.
Makes sense. And data protection itself has evolved quite a bit over the years, hasn't it? Driven by how IT itself has changed.
Oh, massively. The sources talk about 3 big waves reflecting the IT landscape. First was server-centric backup. Back in the day, you mostly backed up individual physical servers, often to tape. Simple, but siloed.
Right. One server at a time.
Then, as applications got more complex, often spanning multiple servers and databases, the focus shifted to application-centric backup, ensuring you could back up and restore an entire application consistently, capturing its database state correctly, etc.
More holistic.
Exactly. And now, with virtualization being dominant, we're deep in the VM-centric backup wave. The focus is on backing up entire virtual machines, the OS, applications, data, configuration as a single unit, often using those image-level techniques we discussed. It aligns perfectly with how modern infrastructure is managed.
So let's talk about the absolute cornerstone, backup and recovery. What's the core idea, and what challenges are providers still grappling with today?
The core concept is simple. Make a copy of your data, store it somewhere else safely so you can restore it if the original is lost or damaged. Basic insurance.
Seems straightforward.
Yeah.
But the challenges?
They're significant. First, the sheer volume of data is exploding. We're talking petabytes, exabytes.
Yeah.
Backing it all up is a huge task. Second, IT budgets are often tight, so cost efficiency is paramount. And third, business demands for recovery are getting stricter, faster RTOs, minimal data loss, RPOs. So providers need solutions that are fast, scalable, reliable, and cost-effective. It's a tough balancing act.
How does a typical backup process work in a modern cloud or virtualized setup? What are the components?
Usually you have a backup client software running on the system you want to protect, a VM, a physical server, an application database. This client sends the data to a central backup server.
The brains of the operation?
Kinda, yeah. The backup server manages the schedules, policies, catalogs, keeping track of what's backed up where, and orchestrates the whole process. It then typically talks to a storage node, often a dedicated appliance, optimized for handling backup data streams, which actually writes the data to the final backup target.
And the target could be?
Lots of options now. Traditionally tape or disk-based backup appliances, virtual tape libraries, VTLs, which emulate tape on disk, and increasingly direct backup to cloud storage, like AWS S3 or Azure Blob Storage, leveraging its scalability and pay-as-you-go model.
You mentioned earlier that old-style backups could really hit the performance of production systems. How does image-level backup help with that, especially for VMs?
Image-level backup is a huge improvement for virtual environments, precisely because it offloads the work. Instead of installing a backup agent inside every single VM, which consumes CPU and memory on that VM.
Which could be hundreds or thousands of VMs.
Exactly. Instead, a separate proxy server handles the job. It interacts with a hypervisor, like VMware vSphere or Microsoft Hyper-V, to take a snapshot of the VM's virtual disks and configuration files from the outside.
Without touching the running VM directly.
Right. The proxy server then mounts that snapshot and reads the data to back it up. All the heavy lifting reading data, maybe compressing and deduplicating it, happens on the proxy, not on the production VM. This drastically reduces the performance impact on your running applications. And you can still restore the entire VM image, or often perform granular recovery of individual files from within that image backup.
Very efficient. Now, what about data you need to keep for ages, maybe for compliance, but you rarely ever touch? Keeping that in your main backup system seems wasteful.
Totally wasteful. That's where data archiving comes in. Archiving is specifically for moving data that's become static or fixed. It's not changing anymore and is rarely accessed, but must be retained for long periods, often years, for legal, regulatory, or business record purposes.
So it's different from backup.
Yes, backup is for operational recovery of recent data. Archiving is for long-term retention and retrieval of historical data. You move this archive data off your expensive primary storage and maybe even off your primary backup systems onto a separate, lower-cost long-term storage tier.
Like cheaper cloud storage.
Often, yes. Maybe dedicated archive storage in a private cloud for sensitive data, or ultra-low-cost public cloud archive tiers like AWS Glacier or Azure Archive Storage for less sensitive stuff, where cost and scalability are key. It frees up your valuable primary resources.
Okay, let's talk about deduplication again. You called it a game changer. Can you unpack exactly how it works and the different ways it's implemented?
Sure. Deduplication is all about finding and eliminating redundant data before it gets stored long-term. It works by breaking data streams down into smaller segments or chunks.
Little pieces.
Yeah, typically blocks of a fixed or variable size. As these chunks come into the backup system, the system calculates a unique fingerprint or hash for each chunk. It then checks a database. Have I seen this exact chunk before?
Ah, like a library index.
Exactly. If it's a new, unique chunk, it gets stored, and its fingerprint is added to the index. If the system has seen that exact chunk before, meaning that block of data exists elsewhere in the backups, it doesn't store the duplicate chunk again. It just stores a tiny pointer back to the original already stored unique chunk.
So you only store one copy of each unique piece of data.
That's the core idea. And the savings can be massive, especially with things like operating system files, standard email attachments, or multiple copies of the same VM template. You often see deduplication ratios of 10.1, 20.1, even higher, meaning 20 terabytes of raw backup data might only consume 1 or 2 terabytes of actual physical storage.
That's huge savings. And you mentioned there are different places this deduplication can happen, source versus target.
Right. Source-based deduplication happens on the client machine itself before the data is sent over the network. It identifies duplicates locally and only sends the unique chunks and the pointers to the backup server. The big advantage here is dramatically reduced network bandwidth usage. Great for backing up remote offices or laptops over slower links.
Makes sense. Send less data. What's target-based?
Target-based deduplication happens on the backup appliance or server after the data has crossed the network. This offloads the processing work from the source clients, which might be preferable if they are resource constrained.
And within target-based, there are options too.
Yes, mainly inline versus post-processing. Inline deduplication happens as the data is arriving, before it's written to the backup storage. Only unique data ever hits the disk, maximizing storage efficiency from the get-go. Post-processing means the data is written to a temporary staging area on the backup device first, and then a separate process runs later, maybe overnight, to scan that data and deduplicate it.
What's the trade-off there?
Inline requires a more powerful backup appliance that can deduplicate at high speed during the backup window, but it saves the most storage space immediately. Post-processing needs more initial landing space for the undeduplicated data, but doesn't slow down the initial backup ingest speed as much. The dedupe happens later.
Got it. So regardless of the method, the benefits of dedupe are pretty clear.
Oh, absolutely. Huge benefits. Lower storage costs, less disk needed, less power, less cooling, longer retention periods possible on the same amount of storage, shorter backup windows in some cases, especially source-based, and significantly lower network bandwidth consumption for backups. It's a foundational technology for modern data protection.
Okay, shifting from backups, point-in-time copies, to replication. This sounds more like real-time duplication. How does it work and differ from backup?
Replication is fundamentally about creating and maintaining an exact, usable copy, a replica, of your data, often in near real time, typically at a secondary location. While backup is primarily for recovery after data loss, replication is often used for failover, rapidly switching operations to the replica if the primary system goes down. It's about business continuity and minimizing downtime, not just restoring lost files.
So it's a live or near live copy ready to take over, and snapshots seem key here too. How do they enable this?
Snapshots are crucial building blocks for many replication and recovery techniques.
Yeah.
As we touched on, a snapshot captures the state of a storage volume or VM at a specific point in time. They're usually pointer-based, meaning they're very fast to create and initially space-efficient.
Because they don't copy everything immediately.
Right. They rely on that copy on first write, KFW mechanism we discussed. When you take a snapshot, it essentially freezes the view of the data at that moment. If a block of data on the live system is about to be changed for the first time after the snapshot was taken, the snapshot mechanism first copies the original version of that block into the snapshot's private storage area. Only then is the live system allowed to overwrite the block with the new data.
So the snapshot preserves the before picture.
Exactly. It ensures the snapshot always reflects the data exactly as it was at the moment it was created, while allowing the live system to continue changing. These snapshots can then be used as consistent points for backup, or they can be replicated to another location.
Okay, so for disaster recovery across sites, you replicate these snapshots or the data changes. What are the main ways storage systems do remote replication?
The two primary modes for storage-based remote replication are synchronous and asynchronous. The choice really depends on your tolerance for data loss, RPO, and distance.
Synchronous sounds like synchronized, no data loss.
Pretty much. With synchronous replication, when your application writes data to the primary storage system, that write must be successfully written to both the primary system and the remote replica system before the application receives the confirmation, the acknowledgement, that the write is complete.
So it waits for both.
Yes. This guarantees that the data on the remote site is always identical to the primary site at the moment of any failure. Zero data loss, or near zero RPO. The downside is performance impact. Waiting for that round-trip confirmation across the network, especially over long distances, adds latency to every single write operation, slowing down the application. It's usually only feasible for short distances and requires significant bandwidth.
Okay, zero data loss, but potentially slower apps. What's the alternative? Asynchronous.
Asynchronous replication prioritizes application performance. When the application writes data, the primary storage acknowledges the write immediately, without waiting for it to reach the remote site.
So the app doesn't wait.
Right. The primary storage system buffers these writes, often in a log or delta set, and then transmits them to the remote site periodically, maybe every few seconds or minutes, depending on the configuration. This means the remote copy lags slightly behind the primary.
So there's a potential for some data loss.
Yes, that's the trade-off. If a disaster hits the primary site between replication intervals, any data in the buffer that hadn't yet been sent would be lost. So you have a non-zero RPO, maybe minutes. But the huge advantage is that it has minimal impact on application performance and works efficiently over much longer distances, hundreds or thousands of kilometers, with less bandwidth. It's a common choice when near-zero RPO isn't strictly required.
Is there anything that kind of bridges the gap or offers more granularity?
Yes, there's continuous data protection, CDP. CDP solutions aim to capture every single write as it happens and log it, typically to a journal volume. This journal allows you to roll back and recover data to literally any previous point in time, not just the specific intervals of asynchronous replication or the point in time of a snapshot.
Any point in time. Wow.
Yeah, it offers incredibly granular recovery. If data gets corrupted at 2.371515 p.m., you could potentially recover the state from 2.37.14 p.m. CDP can operate in either synchronous or asynchronous modes, depending on the implementation and distance, but the key is that continuous journaling for highly granular rollback.
And we're seeing more companies use the cloud itself as the target for replication, right? Like a GR site in the cloud.
Absolutely. Cloud-based replication is a major trend. Organizations replicate their on-premises VMs, applications, and data up to a cloud provider's infrastructure. The cloud essentially becomes their disaster recovery site.
Cheaper than building their own second data center.
Massively cheaper and more scalable. It avoids the huge capital expense and ongoing operational overhead of maintaining a physical DR site. It makes robust DR accessible to many more businesses.
This all sounds incredibly powerful, but also complex to manage. Setting up dedupe, replication, failover. It's a lot for an organization to handle itself.
It really is. Yeah. And that's exactly why data protection as a service, DPIS, has taken off. Cloud providers offer these capabilities as managed services, taking the burden off the customer.
Like backup as a service.
Awesome. Yeah, backup as a service. Backup is a prime example. The provider manages the entire backup infrastructure and operations. There are different flavors.
Go on.
Local backup service, the provider backs up your data that's already in their cloud. Remote backup service, you send your on-premises data over the network to the provider's cloud for backup. You don't manage local backup hardware. And even replicated backup service, which is cloud-to-cloud backup one provider backing up data residing with another provider for extra cross-cloud resilience.
Back up your cloud to another cloud.
Right.
Okay. And then the ultimate offering seems to be DRA, disaster recovery as a service.
Exactly. DRA is the full package.
Right.
The provider doesn't just store backups. They provide the compute, storage, and network resources needed to actually run your critical services from their cloud if your primary site goes down.
So they handle the failover.
Yes. Your data is replicated to their environment, usually encrypted and compressed. If you declare a disaster, your services fail over and start running on the provider's infrastructure. You get a fully functional DR solution, often on a subscription basis, without building and managing it yourself. It's a huge enabler for business continuity.
It really sounds like these services democratize capabilities that used to be only for huge enterprises.
That's a great way to put it.
And just to ground this, our source material mentions specific products that implement these ideas. Can you give a couple of examples of how these concepts manifest in real solutions?
Sure. For instance, Dell EMC Avamar. That's a well-known solution primarily focused on source-based deduplication. It was one of the pioneers in reducing backup data at the client before sending it, which, as we said, is great for bandwidth savings. It handles both OS-level and image-level backups.
Okay, source-side dedupe. What about another example, maybe focusing on replication or CDP?
A good example there would be Dell EMC Recover Point, including Recover Point for VMs. These solutions are built for high-performance replication and continuous data protection, CDP. They offer that ability to recover to virtually any point in time using journaling. Recover Point for VMs specifically integrates with VMware to replicate VMs and enable automated failover, creating those live shadow copies for near instantaneous recovery. It really embodies that advanced replication and CDP capability for critical virtualized workloads.
Wow, okay, what a journey through the layers of keeping things running. We've really taken a deep dive today, haven't we? Uncovering all these intricate parts that ensure cloud service availability.
We really have, from nailing down what availability truly means, those 9 calculations understanding downtime.
Right, and then exploring all those fault tolerance mechanisms, the clustering, the network redundancy like link aggregation and NIC teaming, the storage resilience with virtualization and erasure coding.
And digging into the application resiliency side too, graceful degradation, retry logic, persistent state.
Right.
It's not just infrastructure.
And finally, grasping the absolute necessity of robust data protection. Backup, archiving, deduplication, which was fascinating, and the different flavors of replication like sync, async, and CDP.
Plus, seeing how these are delivered as a service, now BAS and DRAS, making sophisticated protection much more accessible.
So for you listening, what this hopefully gives you is a much clearer picture of what's going on behind the scenes, a solid understanding of how cloud providers and how you, if you're building systems, approach resilience, protect data, and work constantly to keep services online, even when things go wrong.
Yeah, this knowledge should empower you to ask better questions, evaluate services more effectively, and just appreciate the sheer engineering effort involved.
It leads to a final thought, perhaps. We've seen that preventing all failure is incredibly hard, maybe impossible, and definitely expensive. So maybe true business continuity in this digital age isn't about chasing the myth of zero failures. Maybe it's more about building systems that are so intelligently designed for fault tolerance, so good at protecting and recovering data that they can actually thrive because they anticipate and handle failures gracefully.
It's a shift in perspective, isn't it? Building for resilience, not just perfection. Engineering systems that expect the unexpected and know how to react.
Yeah.
Bending without breaking.
So the question for you is, knowing about all these layers of protection, this constant anticipation of failure built into the system, how does that change how you think about the digital services you rely on or the systems you might build or invest in? Something to ponder.